Morning, guys. So welcome to the first big unit that we're going to hit in this physics course. This one here, you can start a fresh new page. We'll label it here Unit 1, and this is going to be kinematics. Essentially, kinematics here is going to be for us the study of motion. So we're going to be visiting concepts like distance, how far, speed, how fast, the time, the acceleration. We are going to see some of those equations that we've been practicing through the last section, but trying to give more of an interpretation in this section here. The goal was hopefully we're now more well versed in terms of the math, in terms of how we deal with sig figs and rounding, things like that, so that when we see problems in this section here, we're already at a better footing. So let's just start off here, study of kinematics here. We're going to start off just differentiating in our world. Quantities can be designated into either what are called scalars or vectors. So if you look at any quantity like mass, time, force, acceleration, they're either going to be under the scalar category or the vector category. Let me give you a definition for this here. Scalars only have magnitude. So magnitude only. They only have a size. Now I remember being scared away by, what do you mean magnitude? If I take a distance, let's say 5 meters, the magnitude is the 5, right? If I have time, let's say 10 years, the magnitude is just the 10. The magnitude is just the size of the number. It's how many you have in that unit. Scalars are things that only have this magnitude. They have size only. Whereas vectors, they do also have magnitude. They also have this number related with the unit, as we're going to see. But vectors, what they add is vectors actually have magnitude, also called size. Right? There's a 5 or a 10, right? Magnitude is size, but they have direction. They actually have a pointing, a heading, right? So that's something that scalars don't have. So let's just start separating our world here. Let's start introducing some things that we know only have size and some things that have size as well as direction. Let's start off measuring different lengths. So we can talk about a distance. So distance, we're going to shorthand this D, right? D is basically the amount of length covered, or the amount of ground that's covered, right? Pull out a ruler and you basically figure out, well, how far is this object from this object? That's the distance. In that case there, we can say D is 50 meters. When I say as magnitude only, again, the magnitude is just this 50 part. Right? Now what we're going to see in this chapter here is we actually have a vector form of distance. We have a form of distance that actually not just tells you how far, but it actually tells you how far in what direction. We're going to introduce this name here called displacement. You may have seen that in some of your junior science classes here. I'm going to put the same D symbol. But because vectors here have direction, they have an arrow to it, I'm going to put an arrow over top of it. So the displacement here, sure, you can say it's the amount that's displaced. In this case here, I'm going to actually say displacement is actually the length between your starting position, start and finish. And I'll give you an example of this very shortly. But that's going to be your displacement. Your displacement might look something like, my displacement is 75 meters, and I'm heading north of east. So not only does it have the size and direction, the magnitude part, right, with the unit, it also has some heading. We're going to qualify this a little bit here. In fact, telling you north of east is not good enough. I actually need to tell you how many degrees north of east. But there we go. It actually has direction to it. The trouble with this here is we're going to be using sort of positive and negative to indicate direction. So sometimes I might just say the displacement is actually positive 75 meters. It's actually that positive that actually tells you forward. It's actually that tells you the sign. If I have a displacement that's negative, now I definitely can't have a distance that's negative, right? The lowest distance can go is 0 meters. When I have a negative, it actually implies that's going backwards. So let me just give you a quick picture of what this might look like. Let's imagine we were in a helicopter. So we're looking down, we're a top view picture, and we're looking down at our classroom. Okay. Let's say one of you are standing at the front of the classroom, one of you is standing at the sort of back corner of the classroom here. So this is our rough coordinate system, north, east, south, west. We're going to see later on the north and east are going to be our positive directions, our west and south are our negative directions. let's say here's the analogy, or here's the experiment. The person at the front of the room just stands there, but this first person here is blindfolded. So when he puts on his blindfold, he knows person number 2 is starting out in the corner. And now what the person's going to do is going to say, all right, I know you're in the corner. I'm going to give you 10 seconds of time. You can walk around wherever you want in the classroom. Right? So I'm going to put on the blindfold. I'm at 0 seconds. I noticed that the guy was standing right there. What this guy is going to do is he's going to decide to go this way, give some numbers to it. Let's say 5 meters. He turns this way, maybe 3 meters, maybe another 2 meters, maybe back down this way, 1 meter, maybe 4 meters over, up this way, 6 meters, right? And let's say the 10 seconds is over, and now the person number 1 takes off his blindfold. From his starting position, right? When I put on my blindfold here, the person was standing over here. I didn't actually watch this person do this motion for the 10 seconds because I was blindfolded. But then when I take off my blindfold, I notice that person has now reached this point in the classroom here. In terms of distance, because distance is a scalar, because distance is just sort of the total number of steps he's taken, the distance d is quite simple. He just goes, well, he went 5 meters in the first leg, and then he went 3, and then went 2, and then 1, and then 4. I don't really care he actually changed direction going between this. 5 plus 3 plus 2 plus 1 plus 4 plus 6. In total, distance-wise, he walked 21 meters. Right? That's sort of like a total, let's just say total steps. And in this case here, I didn't care that he actually changed direction. I didn't care he actually turned this way and he actually turned back the way he came. What I can do now is I can actually give you the vector equivalent of this, which is actually displacement. We'll get into all these calculations later on. Hopefully I've kept this still fairly simple. I can actually calculate the displacement. The displacement is something this blindfolded fellow can actually tell you. Because the displacement just says how much ground is between your starting position and your ending position. So when I put on the blindfold, you were here. You did something in the middle, I have no idea. But when you took off the blindfold, you're actually here. The displacement is actually also a measure of length, but this time it's actually a measure of the diagonal distance from, this is the starting position, this is sort of the initial, and here's the finish, here's the ending position. This is how far you've been displaced. You've been displaced in the northeast direction. It isn't really that you actually climbed over the tables and actually walked this diagonal, but this one here is just a measure of how far pushed over are you. If you had to guess here, is the displacement going to be bigger or smaller than 21? 21 was my total number of steps, but you saw, wait a second, some of the total number of steps were actually backtracking, right? If I go 3 meters north and then 1 meter south, now I actually have only gone 2 meters north. So something tells you here, you're actually not as far away as you could have been because you actually doubled back on yourself here. That's exactly what's going to happen here with displacement. What I've tried to do is I tried to leave this as a triangle for you here. Even if I don't quite have a triangle, I'm going to create a triangle myself. In total, how far have you gone in the east direction? Well, I went 5 meters, and then I went an additional 2 meters, and then I went an additional 4 meters. So in total, the leg of this triangle, I have gone 11 meters in the east direction. Sure, they were separated. I went 5 first, and then I took a north detour, but I'm just going to deal with the x's separately. Now let's talk about the y's. In the y's, you went 3 meters north. We said we went 1 meter back, so now I'm only 2 meters upwards. And then I go an extra 6 meters. So now I actually have that difference is 2 meters. In total here, now we have 2 and 6. So in total, this is now 8 meters. You'll notice what we actually created here. We earlier didn't have this, but I've created a right triangle. I'll do some practice with you later on to actually figure out, well, the total amount of displacement. He didn't actually walk in this diagonal direction, but how far is he from the starting position? Since I was blindfold on to blindfold off, it's actually just given by the hypotenuse. Let's do that while we have it on the board here. So just a squared plus b squared equals c squared. That's why we practice it in our toolkit here. A is actually this 11 meters. In total, you are 11 in the eastward direction. You are 8 meters in the northward direction. That's equal to c squared. 11 squared plus 8 squared gives you 185. And therefore, c is the root of 185. We're going to take the positive answer, give or take, it's 13.6, so give or take about 14 or so. All right? And as we expected, because parts of this motion, you actually came back the way, I went 3 meters north and then 1 meter backwards. Well, that just sort of goes back on yourself. Now you're only 2 meters away. That sort of predicted for us, maybe our displacement isn't quite as big as our distance. if you had done all this distance just straight in one direction, 21 this way, or 21 this way, or 21 this way, and you didn't actually double back on yourself here, we would be displaced. We would be 21 meters away from our starting position. But because this one here, you started changing direction and twisting around and walking backwards, our overall displacement, the overall amount of ground between your starting and ending position, was actually less than your distance. So let me ask you this here. So first, these things here can be different. This one here is the scalar distance, so I'm going to put d for there. When are distance and displacement going to be the same? When is it that your total number of steps that you walk is actually going to amount to being that far away from your starting point? Hopefully you can see that here. Well, if I head in one direction, and as long as there's no change in direction, let's say I walk 21 meters perfectly east. Well, how far is my displacement? Well, because I didn't change any direction, I'm going to now be 21 meters east of my starting point. As long as there's no change in direction, these two should be the same. But in this question here, because there's totally turns and kinks along the way here, it's totally possible that the one that tracks start to finish may actually be different from the distance. So let's make that note there. The distance and the displacement, the scalar and the vector form, are the same if and only if there is no change in direction. Again, that shouldn't surprise you all that much. The difference between distance being the scalar and displacement is the fact that displacement adds a direction to it. Displacement actually cares which way you actually turn. Do you double back on yourself? As long as you don't change direction, if you just head forwards, I'm going to end up that many meters away from where I started. Right? So there's a difference between sort of distance and displacement. I gave you a sort of simple worked out example. I also mentioned I timed this. Right? I was blindfolded here for 10 seconds. What we can do is we can just sort of continue this table here. So far we're starting with scalars and vectors. We have distance, that's the how many total steps. This one here is just straight from start to finish. Let's keep going with that table there. We can also have, let me just relabel it for you here. So scalars and vectors. That's actually the simplest question they're going to ask you. Of these quantities, which is a scalar, which is a vector? We just saw distance and displacement. The sort of corresponding one for speed, we can actually, speed is actually the scalar, and velocity, also used for a speed term. Now we actually see the difference here because I'm going to use velocity for v with an arrow. It's the displacement, it's the one with direction. Speed, I'm just going to use v. Right? So speed, right? As you try to define it here, you try not to use the, it's how fast, it's the speed of the thing, right? You can mention here, well, it's sort of how much ground covered per time, right? Or I alluded to it here, you can say it's how fast you're going. But again, given speed is a scalar, it doesn't care the direction. It doesn't care which heading you're actually going. You can go east, you can go south, you can go upwards, downwards, doesn't really matter. Velocity is also this speed. It's also this sort of, well, how fast are you going? But it factors in that direction. And in fact, what's going to happen is because velocity here is the one with the direction, velocity is actually going to be displacement over time. So velocity is going to be the vector form of distance, right? It's going to be the how far away from start to finish did I actually get, but it is divided by time. This actually gives us our first, what's called our kinematic formula, right? We're in the chapter of kinematics, study of motion. Velocity, by definition, is actually equal to the displacement divided by the time. Again, the arrows just imply here these are vectors. These are the ones that depend on direction. So this is our first basic motion equation. This is the definition of velocity. We actually like, if I can isolate it, let's actually isolate it for d. And then we can go d is actually going to be the velocity times the time. Again, we did that manipulation in the first section. We're not actually changing the formula. We're just playing around with which one is it actually isolated for. So either you can think about this here, this sort of speed or your velocity, this how fast we're going, sort of how fast are we going, will depend on how much ground are we covering, start to finish, and how long it took you to get there. So back in my earlier example here, I found that the displacement was actually 14. Realistically, the person did not walk in this diagonal, right? Realistically, they actually took this path, but because overall, you actually only ended up 14, if you really did walk in this diagonal direction over 10 seconds, what's your velocity? I would then go here for velocity, since I have it isolated for you here. My velocity, I got 14 meters away from my starting point. If it took 10 seconds of time, my velocity is 1.4. Every second for you traveling along this diagonal, you would have traveled 1.4 meters. I know you realistically did not do this diagonal, but between me putting on the blindfold and blindfold off, if I gave you 10 seconds of time and you managed to get 14 meters away from your starting point, it's like you traveled 1.4 meter per second for every second. What about the speed, however? Because speed here is the scalar form, it's the one that depends on distance. Instead of displacement over time, it's actually going to be the distance over time. My actual number of steps was actually more than the 14. I only got 14 away from my starting position, but I actually walked 21 meters worth of steps. So if I wanted to do the same sort of calculation here, speed is also given by distance over time. You can check the units here. Speed is supposed to be given in meters per second, while distance would be meters on top, and time would be seconds on bottom. You divide the two, meter per second. And this time, speed and velocity are also different. My speed was actually 21 meters, right? I actually traveled this path here zigzagging back and forth. It was 21 meters. Time we're going to see as a scalar. That's actually going to be helpful for later on. When I go 21 divided by 10, my actual average speed was actually a little bit higher, 2.1 meter per second. So what that's saying here is, if I look at the actual path I took, I went east, north, east, then this way. If I actually have physically walked 21 meters worth of distance, for me to get 21 meters worth of ground covered in 10 seconds, I actually need to be traveling at an average speed that's actually a little bit higher than the average velocity. Again, we see a difference between scalar and vector because the vector has direction, whereas the speed doesn't have direction. You can think about this formula here. Again, this is going to be called your first kinematic formula. This is the basic motion equation. This is on your formula sheet. This just gives us another lens of it. Instead of where it came from, which is the definition of velocity here, what you can do is you can say, well, how far do I get? So this is the how far. Well, it depends on the how fast, and it depends on how long. If my how fast is, let's say, 50 kilometers per hour, and I do that for 3 hours, well, every hour I travel 50 kilometers, I times 3, that's going to give you 150 kilometers. So that's a basic motion equation. Later on, we're going to be calling this here uniform motion. Uniform motion here implies, so uniform means the same or constant. Uniform motion, it implies so far that there's no acceleration. We're going to come back in tomorrow's lesson to introduce acceleration. When your speed actually changes, you're going to actually cover more ground, right? So we're going to track that acceleration there. So let's just practice through a quick example here. So this is very similar to our toolbox question here, but now we have a little bit more of the interpretation. So let's start off here. A car travels forwards at 6 meters per second for 3 seconds. It then reverses, so it backtracks on itself, okay? It then reverses at 4 meters per second for 5 seconds. I want you to calculate the distance and the displacement. I'll ask you for speed and velocity afterwards, but let's just start off with those two. All right. So there's our standard motion setup here. As always, I like drawing a picture if we can. So we start off with a car. For the first kind of styles of question that we're going to do, we're only going to be dealing with one dimension. So this car is sort of stuck in 1D land. This car can only go forwards or it can go backwards. It can't actually turn. When it can turn, we'll need a little bit of triangle work. We'll see that in a later lesson. But here we have a car. It's going to travel forwards. I'm just going to use forwards. Let's use positive to indicate that direction. Forwards, just for convention's sake here, let's say forwards is actually traveling to the right. That's the positive direction. So we start off, right? Let's say I'm at the starting line here. My car is at rest. It starts heading forwards. What is this 6 meters per second? Well, anything that's measured in meter per second, it's a distance over time. I know it's actually a speed. So we actually know, in this case here at first, your speed or your velocity is actually 6 meters per second. Well, its speed, because it's the magnitude, it's 6. Because of this positive here, it could actually be a velocity. The positive actually indicates to you forwards. So instead of really writing 6 meters per second right or 6 meters per second forwards, I'm just using the positive number. It does that for 3 seconds of time. So like we said, if you know the speed and you know the time, I can know the distance. Later on, it's going to be somewhere over here. It would have covered some positive distance there. Then what it does is it reverses. It goes back on itself. As it reverses, it actually has a speed of 4.0 meters per second, and it does that for 5 seconds. So at first, he's now sort of in front of the starting line. Let's go down here. So now he's going to start reversing. He's going to now go backwards at 4 meters per second. Speed-wise, it's just a number. It's 4, right? It's slower than what it was to begin with. But because I want to actually do velocity, because I actually want to do direction to it, reversing is actually going backwards. It's actually going to the left. What I'm going to do is I'm actually going to add a negative. You're going to see us really sloppy adding negatives, taking away negatives. The negative just indicates for us direction. It just gives us a certain heading. So I'm going to add that negative there. That negative just implies it's in the backward direction. It saves me from having to write 4 meters per second left or 4 meters per second backwards. So negative 4 meters per second, it actually does that for a longer time, so 5 seconds. So it's just keep going backwards here. Here's the question. Calculate the distance. Calculate the total ground that you covered in both of these motions. And probably more interestingly is calculate the displacement. If I blindfolded you at the beginning, I don't actually watch you go forwards. I don't actually watch you go backwards. But when I take out the blindfold, are you in front of the starting line based on these numbers? Are you back at the starting line? Are you behind the starting line? I don't really know. All right? Because there are 2 parts to this motion here, I'm going to study it in 2. Let's do the forwards part here first. So let's go, here's our basic motion equation. The displacement is the velocity times the time. Displacement is the velocity times the time. Your velocity at the beginning was 6 meters per second. Your time is 3 seconds. This gives you here 18 meters, right? After every second, you travel 6 meters. I do that for 3 seconds. I get 18 meters. That's a positive number. That positive means I've gone forwards, right? Second part of the motion. Again, we're interested in calculating the displacement. Displacement is velocity times time. This time, again, displacement has the arrow, has the direction. Displacement is actually a negative 4. So we actually have a negative 4 there. That negative, again, just means backwards. And I do that actually for 5 seconds of time. My displacement actually ends up as negative 20. What's the significance of that negative? The negative, again, just means you go back the way you came. You're reversing. You're actually sort of losing the ground that you gained in the first step. So what we just calculated here is we just saw, well, in the first setup, you've actually gone 18 meters in front of your start. Later on, we actually are traveling 20 meters negative, so 20 meters back the way you came. Now, in terms of distance, distance is the scalar, right? Distance, I'm going to remind you, scalar. Distance doesn't care. You actually went forwards and then started turning around and going in reverse. For distance, you just said, okay, I traveled 18 meters, and then you travel an extra 20 meters. I don't really care. It's backwards. In total, you've traveled 38 meters. Fine. Right? That's how much literal ground that you covered. Displacement, however, displacement is the vector form. And because displacement is a vector, it actually has direction to it. Displacement now says, I go 18 forwards. The 20 was actually going the opposite way. To show you that was opposite, it's actually using that negative symbol. Again, this one here is to the right, which is positive. The negative means to the left. So overall, your total displacement is just negative 2, right? So that means from when I blindfolded you to when I take off the blindfold, my car is not only, it's not anywhere in front anymore, it's actually 2 meters behind my starting point. From where I started, right, I actually went forwards, I actually came backwards. By the time I end, I'm actually 2 meters in the negative direction. I'm actually 2 meters behind where I started. Realistically, the car never did just travel backwards 2 meters. It actually went forwards, it actually went backwards. But over the course of both motions, because I sort of double back on myself, in total, how far you push from your starting position, you're actually 2 behind where you began. With that, it's fairly easy then. Let's say part B of the question. We can calculate what's the average speed and what's the average velocity. Right? Average speed, average velocity. So we just go straight from the definitions here. Speed is the scalar, distance over time. Velocity is a vector, displacement over time. These would be the same if there's no change in direction, but definitely there is a change in direction this time. We're just going to do a quick division here. Well, the average speed, now truth be told, your speed was 6 and then it was 4. Why can't I just go 6 plus 4 divided by 2? Right? If I do a simple average like that, usually that would work, right? It usually give me some average speed, but you have to remember, I'm not traveling these for the same time interval. I do go at my faster speed, but a shorter time period. I travel at the slower speed for a longer time period. That sort of prevents me from being able to do something simple like, 6 plus 4 divided by 2. That would assume that I'm traveling equal times for this motion. What we're going to do is easier because we actually have the distance here. We actually say, well, I actually traveled 38 meters worth. I did 8 seconds. Sure, some of it was at the fast speed, some of it was at the slow speed. My average speed is 38 divided by 8. This one gives you here 4.75 meters per second, or 4.8 meters per second. How about the velocity? The velocity, in a similar manner, velocity is like that blindfold analogy here. I didn't actually watch you go forwards and then actually come back. All I know is after 8 seconds, you happen to be 2 meters behind you. So if this car instead didn't go forwards and then backwards, if it instead just slowly eked its way backwards, if I give you 8 seconds of time and you end up 2 meters away, what average velocity would you have? I end up 2 meters behind where I started, negative 2 meters. It took me 8 seconds of time to do the travel. Your average velocity, again, it's different. Your average velocity is only 0.25. Notice the car at no point in this motion did it actually travel this slow. But what this is saying here, let me just translate this for you here. For the car to end up 2 meters behind the start after 8 seconds, it traveled negative 0.25 meter per second, and that negative means backwards. Just like in the first example, it's not like the person actually walked over the diagonals and actually climbed that for the displacement. In this case here, we actually, on average, are traveling backwards, 0.25. Again, these two are different. They would be the same if there was no change in direction, but definitely there is a change in direction for this problem here. So I'm going to leave the lesson off there. We're going to do a quick practice question of this kinematics basic motion in the next lesson, and then we're going to throw in acceleration. It just makes the equations just a little bit harder, but we'll take it up from there. Thanks, guys. Take care.